Afternoon, sir. My name is William, matric number 293723. Now I am serving the breakout of the study. In separating at the end, Joseph Louis Lagrange discovered the key discovery of Lagrange multiplier by using the concept of virtual velocity to solve the static problem from the mechanics book with the constraint. In 1811, Lagrange emphasized the significance of his multipliers for the restricted optimization in his second edition of his mechanics. Therefore, Lagrange multipliers is able to handle the constraint-based optimization problem. Optimization is the practice of making changes to an existing process to make desired result more likely to occur and the undesired consequences less likely to occur. In a nutshell, the usefulness of Lagrange multiplier has been covered in many fields, especially in engineering, computer science, and economics. Lagrange multiplier is able to cope with the problem that more than one variable compared than the normal optimization method. So Lagrange multiplier is the preferable for us to apply to find out the best solution that we wanted.
Next, the key concept of this assignment is about the Lagrange multiplier technique, which has made many contributions in solving actual optimization problems in given several control factors. The optimization problem is to maximize or minimize a function constructed based on data with the combination of long range by systematically substituting the input within the range provided and computing the greatest or the smallest value of output. There are three fundamental elements which are objective functions, collection of variables, and set of constraints. We have focused on the efficiency of output in generating hydro energy and optimization of time spent using the Lagrange multiplier technique in this assignment. There are three objectives for this assignment. First is introduce and briefly explain the application optimization problem using the Lagrange multiplier method. Second, which is explore the application of Lagrange multiplier in solving real-life problem. And the last is construct a connection between a conceptual framework and the theoretical framework of multivariate calculus.
Now, I will continue to present the methodology part. 2.1 Method of Lagrange multiplier. The Lagrange multiplier method is a strategy for determining the extreme values of fsy when the point sy is constrained to be on the level curve gsy equal to 0, where fsy equal to c, c is a constant along the level curve. It is to determine the biggest value of c such that the level curve fsy equal to c crosses gsy equal to 0 so that it can maximize the fsy subject to the gsy, and this curve just touch when they share a tangent line and normalize at the place where they touch xy coordinate are the same. Therefore, the gradient vector are parallel. From the chain rule, we have df equal to partial derivative f over partial derivative s ds plus partial derivative f over partial derivative y dy equal to 0 as the first equation. For the second equation is the dg equal to partial derivative g over partial derivative s ds plus partial derivative g over partial derivative y dy equal to 0. The second equation is multiplying by the lambda and adding with the first equation, so it becomes partial derivative f over partial derivative s plus lambda partial derivative g over partial derivative s ds plus partial derivative f over partial derivative y plus lambda partial derivative g or partial derivative y dy equal to 0. If the function f is to be extremized and g denoted as the constraint are the function of the three independent variables x, y, z, therefore partial derivative f over partial derivative s plus lambda partial over derivative g over partial derivative s equal to 0 for partial derivative f over partial derivative y plus lambda partial derivative g over partial derivative y equal to 0, and lastly partial derivative f over partial derivative z plus lambda partial derivative g over partial derivative z equal to 0, so it is concluded that gsyz equal to 0. 2.2 Second partial derivative test. Second partial derivative test can be used to find the minimum or maximum of f. The function of two variables must be always continuous at the point x and y. Let z equal to fxy. Partial derivative of f respect to x equal to 0. Well, partial derivative of f respect to y equal to 0. Therefore, dxy equal to second partial derivative of f respect to x times with the partial derivative of f respect to y minus partial derivative of s and y bracket square. Therefore, the result and interpretation are shown as below. For the case 1, if d more than 0 and second partial derivative of f respect to s also more than 0, then it can conclude the function f has a local minimum at the point s and y. For the case 2, if d more than 0 but the second partial derivative of f respect to s is less than 0, then it can conclude that the function f has a local maximum at the point s and y. However, for the case 3, if the d less than 0, then f function has a starting point at the point sy, and function fsy is not a local minimum or a local maximum. Lastly, for the case 4, if d equal to 0, then the test will be inconclusive, which means function fsy might be a local minimum or local maximum or a starting point.
Now I'm going to talk about the example 1, which is about the utility maximizations. In this scenario, a university student who has 12 hours per week to spend their time to play video games and sports. We assume that playing sport acquire 1.5 hours, while playing video game will only acquire 1 hour. Hence, his goal is to maximize their utility subject to time constraints. Given that the utility function is equal to ln g plus 3 ln s, and the time constraint is equal to g plus 1.5s less or equal than 12. And it's because that the satisfaction increase in both g and s, and we can assume that the student will spend all of the 12 hours in one of two activities, and thus we can say that the constraint will bind. So we also can write the time constraint as g plus 1.5s equal to 12. In order to find the optimizations of the utility, in this case, Lagrange multiplier method has been applied due to the existence of the time constraints. The formula of the Lagrange multiplier is equal to f of g and s plus lambda g of g and s, while the f of g and s is the utility functions and the g of g and s is the time constraint functions. So we need to sub these two functions into the Lagrange multiplier equations, and we'll get f of g and s and lambda is equal to ln g plus 3 ln s plus lambda g plus 1.5s minus 12. And after that, we need to maximize the Lagrange with respect to g, t, and lambda. So we can begin by finding the partial derivative of f of g and s and lambda with respect to g, t, and lambda. After finding the partial derivative of g and s and lambda with respect to the g, t, and lambda, we need to solve the equation using simultaneous equation in order to find out the value of the g, s, and lambda. In this scenario, we have calculated out 4 simultaneous equations. The first one is 1 over g plus lambda equal to 0. And the second one is 3 over s plus 1.5 lambda equal to 0. And the third one is g plus 1.5s minus 12 equal to 0. And when we use the equation 1 minus equation 2, and we will find that the s is equal to 2g, this is become our fourth simultaneous equations. And when we substitute the equation 4 into the equation 3, and we will find out that the g is equal to 3. And at last, we substitute the g equal to 3 into the equations 4, and we will get that the s is equal to 6. And hence, our critical point is 3, 6. So in short, we can conclude that the utility maximization for the student to spend on playing video game and sport are 3 hours and 6 hours respectively, and this can show that these two time commitment to do indeed exhaust the 12 hours available for sport, since we can prove it by substitute the s and g into the time constraints, which is 3 plus 1.5 times 6 is equal to 12. So in order to determine the local extreme value of utility for this scenario, we will carry out the second derivative test. and the result of secondary test of functions is shown below. After finding all the value of second derivative, we have to substitute it into the equations, and we found that the answer is 1 over 108, which is larger than 1. So we can say that the utility functions is a local maximum since the d has a positive value.
Good afternoon, doctor. My name is Ng Wai Kuan, metric number 292354. Today I'm going to present about application 2, which is hydroturbine optimizations. Well, before we get into this kind of physics problems, we have to first give a brief conceptual idea regarding what we're going to learn. Okay, first talk about the hydroturbine. First, we have to have an idea regarding the Bernoulli equations. The Bernoulli equation, as shown below, it means that over a streamline, it means that the fluid connected, they have this kind of identity over each point. Uh, the P over here, it means that the pressure of each point. And the second term is look like the P, but in fact is the rho is called the density of fluid. The V is the velocity of fluid, and H, officially in physics we call about relations, but it's just the height of the fluids. Okay, the G is a gravitational acceleration. C is a constant, provided assumption that the fluid is incompressible, frictionless, with constant pressure, kinetic energy, potential energy, and so on. Because we have to know that each fluid will have a different flow coefficients. For example, the honey will be very sticky. After we have a fundamental understanding about our physics theory, then we go into scenario analysis. Consider a hydroelectric generating station that consists of three different hydroelectric turbines. The water is piped from a dam to the power stations. Each of them generated an amount of electric power with their particular power function respectively. The incoming water can be distributed by the power station in different volume to each turbine. The following are the quadratic model in power function for each turbine according to the experimental data combined with Bernoulli equation. It means that today they got three kind of different turbine with quadratic model in power functions. What we're going to do is we have to determine the distribution in order to get the maximum energy production with assist of the constraint. Now we come into calculation part. First, we have to construct two functions. One of function is called the objective function is equal to a sum of the energy production equation as shown below. Another one, we have to construct the constraint functions. Then we combine it, it becomes the Lagrange function as shown below. Then we calculate the partial derivative of Lagrange function respect to each q and lambda. We set the gradient equal to 0 in order to find the maximum. In the end, we will have four equations with four different unknowns. After a long process, we finally solve the Q1, Q2, and Q3 in terms of a total flow of distributions. For example, today there is an incoming flow of 3,000 meters cubed per second from the dam. What we're going to do is substitute the 3,000 equal to the Qt. Then we will find out the distribution of Q1, Q2, and Q3 respectively. We substitute Q1, Q2, Q3 into our total energy production function. Then we will get the maximum energy generated by the power stations. In order to test for the maximum, we use the trial and error as shown in the table. And be done.
So, to conclude this, we will say that Lagrange multiplier method is an advanced measure of solving the optimization problem and is a strong mathematical skill in solving inequality problems. That's all from us. Thank you.